Hello, welcome to this webcast from Enea Software. My name is Nigel Day and I'm Product Manager for Polyhedra, Enea's family of database management products. This webcast is the second of a three-part series on the topic of active queries, one of the features of Polyhedra that makes it particularly suited for use in real-time embedded systems. The first webcast introduced the Polyhedra product line and explained why traditional techniques do not properly address the needs of systems where a real-time database has to handle multiple clients that have to detect and react to database changes as fast as possible. This part describes features of our active query mechanism that keeps clients up to date with minimal complexity, low latency, and low load on the database management service. So, without further ado, let's introduce what we mean by active queries. Initially, an active query behaves much as a normal or static query. Thus, the application specifies the query by means of an SQL select statement, and the client library sends this to the database server. In response, the server will execute the query and send the result set to the client, where the application code can then inspect it. However, as the request was flagged as active, the server does not forget about the query. Instead, it keeps it open, and now, in theory, any time the database is altered, the server will check to see if the active query is affected. If so, the server works out what's the minimal information that needs to be told to the client to bring it up to date, and sends this as a delta message to the client. Of course, the client may have set up many active queries, so the delta message also identifies which one is affected. It is important to note that a delta is not a notification that a change has occurred. Instead, the client application has been brought up to date, so there is no need for it to launch another query just to see the current state. Also, active queries do not end when the first delta is sent. They remain open until explicitly closed by the client, or the connection between the client and the server is lost. During the lifetime of an active query, the client may get a large number of deltas, each containing the information to bring it up to date. Of course, it will be very inefficient to examine each database change to see if it has affected any of the outstanding active queries. And so there are various optimizations done inside the server to speed things up. The main performance optimization comes from the fact that code modules inside the server can make use of the trigger mechanism provided by the core data store module running inside the database server. Thus, if an active query is established on a single record of a table, identified by its primary key, the code handling the active query inside the server can set up a callback function, and this will only get triggered if that row is changed. The query handler can then find out which attributes are changed, and, post-transactionally, it can send a delta to the client with the latest values of those attributes. Of course, if the transaction fails, there is no need for a delta, as the database will have rolled back to the pre-transactional state. As well as row triggers, the active query support code can also make use of column and table triggers, so that the more complex queries can also be handled efficiently. The next optimization we added was a way to cope with slow clients. If the database server notices that a client is not keeping up with the deltas it is being sent, it enters a delta merging mode. In essence, it stops sending deltas until the client catches up a bit, and then sends it a catch-up delta reflecting the current state. This means the client is not necessarily told of each and every change, but instead is simply kept up to date. Another performance optimization allows the client application to capitalize on the delta merging mechanism by specifying minimal intervals on its active queries. Thus, a graphic application can ensure it does not get updates for on-screen values too fast for operators to read them, no matter how fast new readings are being pumped into the database. Used sensibly, this reduces the workload of both the client application and the database server. Taken together, these improvements make it possible for a database server to handle many thousands of open active queries without being overloaded. Having implemented an efficient way of monitoring selected parts of a database, we then decided to make the mechanism bidirectional. If using our ODBC API, for example, the application code can modify fields of the local copy of the result set, and our client library will automatically generate a transaction to cause corresponding changes to be made to the database. It is even possible to batch up changes and get them committed as a single transaction. In fact, such a transaction could involve multiple active queries. The question arises, however, about what to do if the database had been about to send a delta at the time such a transaction is sent through. The answer we chose was to adopt an optimistic concurrency approach. If the change requested by the client application clashes with a change being reported in a delta, it is assumed that the client might be operating on old data, so its changes are binned. When checking for clashes, the granularity is down to the level of individual fields. Thus, it is possible to alter the alarm limits associated with an analog sensor, even if the value field of the same record is being continually updated with new readings. A more recent extension to the active query mechanism has already proven very useful in certain SCADA applications. If, for example, a number of remote sensors are connected in via cellular network technology, then it may be impractical or expensive to keep all the connections open all the time, and instead one could adopt the strategy of polling individual points infrequently. If an operator wants to monitor a particular sensor in real time, this latest extension means it's now possible for a helper application outside the database to detect when an active query is started on such a sensor's record. The helper application can then ensure the sensor is polled more frequently while the active query is open, and drop the polling frequency back down again to its normal value when the active query is terminated. By providing a way of centralizing the management of the polling frequency into a helper application, the new Polyhedra functionality allows system designers better control, and they can more readily tune the behavior to meet the needs of individual installations. The new mechanism is configured by creating records in a special database table. The third and final webcast in this series will show a live demo of active queries and then look at the code underlying that demo. In the meantime, if you want more information about Polyhedra or to download a copy of the white paper describing active queries, please visit our website.